Zaid Tasneem from Rice University. He has done a really interesting piece of research here on how you can train neural radiance fields with decentralized methods. So I'm going to hand over to him. He can tell us all about the paper. This particular piece of research was done with Flower. And so, yeah, we're happy to see people benefiting from the framework. So over to you, Zed.
Thank you, Nick. Let me share my slides first. And also, I'm so happy that while working on my problem, I got to use Flower because it really solved like a huge part of my research. So let me start with, can you see my screen?
Yeah, it looks great.
Oh, yeah, so that sounds good. So yeah, so today's talk is about decentralized neural radiance fields. And first of all, let me introduce myself. I'm a final year PhD student at Rice University. And apart from working on like federated learning, I've also like my dissertation is about privacy-aware computational cameras and frameworks. So I have other works that are like interested more towards imaging and how to image in privacy-aware fashion. But I think this is a very interesting problem of decentralized, computation and how we can add that into the problem of neural radiance fields. So let me start with like first the problem statement. So the problem statement we defined for today's talk is, can we use like personal images to learn immersive representations at a global scale? And the idea comes from this notion that there are geotagged images of millions of scenes around the globe. They are siloed in personal camera rolls. As you can see, the multiple users have visited the same one of these millions, scenes, and they have taken different viewpoints of the same like scene. And we have to come up with this talk. We have to come up with an XYZ algorithm that does immersive views of millions of scenes. So you can like by immersive views, and you mean that you can like pretend that you can roam around in the scene as if you were actually there. So let me motivate the problem slightly more. So the question I'm going to ask is, can we render the world with high fidelity? And by the world, I mean all of the world with high fidelity. So imagine sitting in your living room with your $3,000, Vision Pro headset, and let's say you want to virtually travel the earth. You want to go to Boston. You want to basically see what the streets of Boston is like. You want to like move around them, walk around them, see how they're like during night. You want to walk into like a restaurant in Boston, and you want to like kind of experience sitting, in your couch, how the world feels like. So how does it happen? As Nick had mentioned earlier, there's this powerful new algorithm came out like a few years ago, neural radiance fields for 3D representation. And all of the previous renderings were created by some version of this NeRF algorithm. And so basically what are NeRFs? NeRFs are multi-layer perceptrons or neural networks that take a bunch of images of a scene and they try to learn a representation of that scene. So in this case, there's this like scene on the left, which is like a Lego excavator. And then the idea is that what the users have or what the people have are like just the image views, the images that people have captured. And what the algorithm does, it basically renders per pixel a ray that shoots across the scene volume. And from that, this neural network is queried for different points along this ray. And the neural network has to predict the color and density at each point. And you do it for all the rays in your images. You sort of basically can plot the PDF distribution, which is basically color. You can see the color showing up in the PDF, plus also what is the density of points along this ray. And then you can implement a very fast volume rendering algorithm that sort of converts this like ray PDFs into like what the pixel value should look like for that particular pixel. And since you have the images already, you know what the ground truth pixel value should be like. So you take a rendering loss, which is just an L2 loss, and then that way you can learn the neural networks that represent the 3D scene. So NeRF algorithms are basically like, recipes you can take basically that take a bunch of, ingredients, and the ingredients in this case is a visual data as input. And they can, also be served on different platters. So, rendering is also a problem in neural networks. Once you learn these NeRF algorithms, how do you render for, final applications like on your Apple Vision Pro headset or your mobile devices? There's a lot of work that goes into both the aspects of NeRF algorithms and rendering, like that handles constraints like computing, storage, and how do you learn with only few shots, and if you have inconsistencies in your images. but not a lot of work is done on the ingredients of the dish itself, which is the volume and diversity of data that can be used. So the more the volume you have, the more scenes you have, the more nerves you can create. And also, because you're going to use these data now, privacy concerns come if you end up using users' personal data. So let me just talk about what are the sources of visual data. So some are public images on the internet, like people always post where they're out, where they're like visiting on Instagram, Facebook, and other avenues. On the right, you can see these are some curated images by Google Maps about this particular bar in Houston, Texas, and basically you can see there's a bunch of images it has. But the interesting part about public images is that only 2% of the data that we actually capture, 2% of all the images that we actually capture on our phones and end up on the internet. The rest of them remain siloed in our personal devices. There's another form of data which is enterprise data. So Google is always trying to send out this Google Maps card that trying to collect data across the world. And then also they send out people with the backpacks having camera rigs on top and sort of collect more and more data about the world. So this is good, but at the same time, it's very expensive because these sensing devices cost a lot, and then sending people out and drivers out cost a huge labor cost. The last one that we have not actually looked into, which is private user images. So everyone has a camera phone, and on average, we take around 2 to 3 images per day. We don't share it on the internet. People usually keep them private, and they end up either on the Apple and Google Photos app or just their camera galleries. So what can we do with these images? So what do these images contain? The camera rails contain geotagged and time variable images. So on the left, you can see user one's Google Photos heat map, where they have visited this particular bar, as I mentioned earlier, on 16 December in 2021. And on the right, you can see another user who has also visited the same bar, but on a different time. Now imagine having millions of these users for millions of scenes, and what can we do with these scenes is the problem statement we had. So yeah, we have to come up with this XYZ algorithm takes these kind of users, their data, and create NeRF renderings of those scenes. But then what should be the key requirements of this XYZ algorithm should be? So one should be photorealism, because you're trying to sort of create the same world back. So it has to be photorealistic. Second, because now you're kind of using people's personal camera rolls. So privacy concerns come into the picture, and you have to be really, really cognizant of those privacy concerns. Third is scalability. And this is where the decentralization aspect comes into play. As Nick has mentioned, you can sort of do these centrally. You can try to learn all of the scenes, scenes centrally, but at the same time, you end up spending a lot of compute on your own. So how to scale up to millions of scenes, how to make sure when you scale to millions of scenes, how well does your algorithm scale up? So I'm going to mention again the challenges of learning now some personal images. So the challenge of privacy. First is the challenge of privacy. So user images may contain personal content that users are hesitant to share publicly. As you can see, in this user image captured on a personal device, it features both scene-specific global content and the one that we want to actually render, and the user-specific, such as the monument, and user-specific personal content like the individual captured in the frame. Secondly, as I mentioned, learning NeRFs from millions of scenes in a centralized fashion is computationally intractable. Training a NeRF for a single scene requires 100 teraflops of computing power. Depends on the scene, but usually that's the average figure. And performing these computations centrally would not scale for millions of scenes, because you require 100 million times more of this compute. This is where a privacy-aware decentralized approach, which I introduced right now, DecentNeRF, comes into play. It can create photorealistic renderings as shown in this video without requiring users to share their raw personal data with the server. Furthermore, DecentNeRF demands 4 orders of magnitude less server compute per scene, making this solution scalable for learning NeRFs at a global scale. So before we present DecentNeRF, let's look at some possible solutions and why they don't work. So in this case, you have multiple users. They have gone to a particular scene. They have images from multiple viewpoints on their user devices, as shown in the left. The problem that we want to address is there's a server that wants to create a NeRF using these user images. So the obvious solution is centralized neural network fields, which is send all the data onto the center server and sort of train a NeRF algorithm. And you can see the NeRF algorithm, is photorealistic. It looks, kind of reasonable. But at the same time, because you send all the data onto the server has basically seen all the images that you have, so it's not privacy agnostic. So it's like it's not privacy aware. And the third thing it's failing at is that for one scene it works, but then if you go for like millions of scenes, then you come to the same problem of scaling. So centralized solution might not be the best solution that we want. The second thing that folks over here especially would mention is like, oh, why don't you do federated neural radiance fields? So these actually exist, like, but then they don't actually work in real life. So what in federated learning happens is that instead of sharing the data, you share either representation of data or like some neural network that learns a task on the data. So you basically share that user neural network with the server, and then the server can you send it, the server sends it back. You keep doing this back and forth of like, taking the average of the server and then relearning like locally on the local device. How does it well? And then you can see this NeRF aggregated on the server, learn using federated neural network fields. Doesn't work that well. The reason being it's not photorealistic. A lot of a lot of personal content starts showing up. Secondly, it's also not privacy aware, because even though you've only sent the representation of the data, that data, the 3D scene data itself contains like personal content, and you have not made sure that you have taken all the personal content. But the good thing about it, it's decentralized. So in this case, all of the learning happens on the user side. So all the training cost is borne by the user, while the server only bears the cost of just aggregating these MLPs together. And these could be very minute compared to what the training cost of actually learning a NeRF is. So here we introduce, DecentNeRF. It's a three-step approach, drawing concepts from NeRFs like personal global separation, from security like secure multi-party computation, and also fair learning, like trying to optimize what the user weight should be for the global model. So first, we present the first key insight that helps us, achieve this thing, which is one is personal and global content can be separated. So you can see that in this particular user image is like highlighted by in red. The personal content is there, but what you notice is that personal content is transient across users. So this personal content would not be like sort of available in user devices because this picture was taken at a different time. While the global content is static across users. So global content would be there no matter which user comes and takes an image. So it's going to be static across user. So what we do is we employ two MLPs. One MLP, one neural network, basically captures the personal content, and the other captures the global content together. We do it for multiple users. And in this way, we sort of only share the user's global MLPs. So this way, only the user global content gets shared to the server, while the personal content remains local to the user devices. Another thing that we notice is that data is heterogeneous. We talked about in federated learning, like IID, non-IID, does it work for IID settings, or does it work for like non-IID settings or not? So in general, in like real world scenarios, data is always like, non-IID. So the users can vary in terms of like, number of views, number of disparity, user to scene content, like maybe one has a lot of occlusions, one user doesn't have a lot of occlusions. So instead, unlike typical federated learning, where each user's contribution is like, let me go back. Each user's contribution is like equal, as noted by the equally weighted arrows towards the server global MLP. We can sort of come up with introduce a novel federation procedure where the per user scaling is learned implicitly to maximize the visual fidelity. So we call it a learned federation of global MLP weights, and it improves photorealism. And the way it's learned, and I'm not talking about this slide in this like talk, but basically, if a user performs very well on its particular task of rendering its own content, then we start valuing it more and more than other users who start failing on their rendering performance. The key insight number 3 is that basically the user global MLP has personal content. Even though we do the separation on the device itself, we found in this particular graph that in the initial rounds, here you can see on the y-axis the personal content measure in terms of PSNR, and over the x-axis is the federation learning rounds. How over the length of aggregation, how does it perform? And in the blue you can see the user global MLP. So a particular user, let's say the blue user on the top left, that's the user that we're trying to see. And then you can see initially it has a lot of personal content. But then overall, it starts like reducing its personal content, and the personal MLP starts capturing that personal content back. The reason is that initially, all of the users would not know what is global or personal because they don't know what the other users think is personal and global. And that only happens due to aggregation. So in the initial rounds, even though the global MLPs from the user side might leak information, we want to use something like secure multi-party computation to prevent the server from accessing these individual users' MLP. So the key idea over here is this: is like if the server can see the individual user's global MLP, it can know what the personal content is, but the user can only see the average out like global MLP. So aggregation of all the users' global MLP. And now in this case, you get an average MLP, and that average MLP doesn't leak out information as badly as the individual MLP. So this is what the decentralized DecentNeRFs looks like. Again, three different approaches, three different key innovations: personal global content separation, using uses of secure multi-party computation for maintaining privacy, and then learned federation of global MLP weights to improve visual fidelity. So how does it look like? In terms of privacy, so privacy in general, like people try to define it in like a binary term, something is private or not private, but then in theory, it's kind of like a gray area in terms of like how do you measure privacy, and it depends on what application you have. So in this particular case, we measure privacy leakage as server's ability to reconstruct the personal content. You can see for a centralized NERF, because the personal images are shared, you can almost server knows exactly what the personal content is. For federated NERF, even though we're sharing the representation, from the representation itself, we show that we can sort of reconstruct what the personal content looks like. So in this case, it's kind of does like, you can't really say who the person is, but you all know what the person is doing. They're raising their hand, what they're wearing, all of these privacy details get, like shown out. But in our case of DecentNeRF, we have like minimal personal content rendering. So even in the first initial rounds where the global content was very high, we see in the average MLPs, there's no personal content at all. And this is also verified by running a person detection across all the views of all the training views across all different federation rounds. And you can see federated NERFs, the personal content, number of person detection done on these images by a person detection network improves. But for DecentNeRF, the value is very, very minimal, almost zero. It's also scalable. So here we're going to talk about how DecentNeRF like learns photorealistic renderings with like 4 orders of less server compute than a centralized approach. So here you can see DecentNeRF's renderings. Here you can see federated NERF, which is a naive decentralized approach. And you can see NERF in the wild, which is a centralized approach. In terms of reconstruction quality, we do as good as a centralized approach. The PSNR degradation is not much. At the same time, the server compute we have is around 5 billion flops, which is comparable to what the naive decentralized approach would do, but much, much better than, what a NERF in the wild 200 teraflops, sort of like training cost it requires. And also you can see in these areas of where personal content is present, actually ours do the best. It kind of doesn't show any personal content at all, while even like you can see blobby artifacts both on FedNeRF and the centralized NERF. So there's some more results about crowdsourced data. Here you've taken 2 more images where they're basically crowdsourced by people, and then you can see on the top, so the rightmost two like columns, you can see DecentNeRF and the ground truth performance, and you can see federated NERF kind of doesn't reconstruct these features back, especially the details. Over here, this becomes very blurry, and in this case, you're able to like get more of these like details back. Obviously, these were done with like very small, like very vanilla NERFs. So these problems can be like photorealism can be improved if the axis that you want to improve is photorealism. You can do much better NERF algorithms than the vanilla NERFs that I've shown this. This is also sort of like saying that in terms of photorealism, like the performance drop is not much across multiple measures of SSIM, LPIPs, and PSNR, especially considering if you were doing that for a naive decentralized approach like federated NERFs. So decentralized approach like DecentNeRF would perform much better. So again, along with photorealism, our DecentNeRF prevents leakage of personal information. It's also scalable. It requires 4 hours of less server compute. But where can we use this, this DecentNeRF? So you have this notion of like geotag images on users' personal camera rolls. One thing that you can improve is like Google Maps immersive views for indoors and streets. So basically, this is something that Google itself has like said that they want to do, whereas basically you want to go to sort of like a new restaurant. You don't know what a restaurant looks like. I mean, I can look at the images, but it doesn't really give me the vibes of that place. Like, can I take my colleague for dinner over there? Can I take a date over for dinner or not? So in this case, you can sort of like, look at them in 3D and kind of figure out what the vibe of the restaurant is. So currently, how Google, imagines this will be done is basically the 5 steps to it. But one of the important part is photo capture. In this case, a trained photographer goes to a venue and follows a strategy to capture these things. So what DecentNeRFs can come in and do is basically sort of come in and sort of like take the images that are available in user's personal phone, and then sort of replace this like sending of this highly trained photographer to like capture these images, and that can be replaced by just using like crowdsourced images. Another is basically this Google Maps updating. So according to Google, it's like, one of the most difficult features to keep up to date. So sort of like Google tries to take new street view photos in major cities once a year. And then if you have crowdsourced images, you can sort of like these NeRF renderings can help you sort of update these maps so they don't fall behind. Another thing that you can do is sort of like you have multiple, you have multiple recordings, like, videos on your phone of concerts on different like memories that you have, and you can employ these dynamic NeRFs. So I show for only for static scenes, but the potential in the future is to do for like dynamic NeRFs where they, instead of just doing 3D representation, they can do 3D plus time representations. And I'm sure it for a very small scenes, like you can do it for city scales size, and then that can help you in terms of, urban planning and development. This is what I showed for my case is phototourism. So I've shown like 3 phototourism sites where you can like sort of like put on your headset and kind of, roam around roam around those things. So I want to like thank my collaborators. So at Rice University, my advisor is Shubh Piragwan, and then another postdoc who is actually at MIT right now is Akshat. And at the MIT Camera Culture Group, I was working with Ramesh Raskar's group with Kushal, Abhishek, and Praneeth, Abhishek and Praneeth are very good at like, I think Praneeth and Abhishek came up with this idea of split learning as opposed to like federated learning. So they were very helpful to like, talk about it. Also, at the same time, I would like to thank Flower Labs and Javier for like, helping me out, because I think when I was starting with this project, I had no clue about federated learning, and then just having access to something that's so open source and so easy to use was really, really helpful. So that's the reason like, Flower Labs is like an integral part of this project. Okay, I'm happy to take questions now.
Thank you for that talk. It was I really appreciate the way that you paced that talk out and kind of walked us through motivation, the technology, and also the use cases. So yeah, thank you. Great talk. If anyone in the audience wants to ask a question, raise your hand. I'll check out the Slack. But yeah, let's see what's out there question wise. Oh, Javier's got a question. Okay, over to you.
Yeah, I have, maybe it's a very easy question, but well, first of all, I really like the presentation. I think also having all those visualizations of the results made it's super nice to showcase how good your method works. So that's really nice to see. My question is about what has to change in how the framework works, so you can, for example, recover some of the details in this, in the results of the NeRF. I know there are some techniques, or there were some techniques a while ago, like maybe using a gun to hallucinate some details and things like that. How do you see this? That could be done maybe in Excel.
So I think it's a very interesting question. So I think any pipeline currently with the system that I developed will take some more innovation to get in. But at the same time, you can, let's say, can give you an example of this case where you want to sort of create this like, let's say, where's that figure? Like this vibe of this restaurant. That's the problem that you have, right? You want to create this vibe of the restaurant. But then you can see that like doing from crowdsourced images, it would not be possible because those will be blurred out because the chairs would have moved in like 3 years time, so those things, if you want to reconstruct, would not be working. So things like where you can sort of like look at one example of a chair, in one of these images, like the most current one, let's the restaurant has not changed the chairs in the most current one, and sort of start rendering based on, like what the using GAN-based methods to sort of start rendering those things instead of like trying to learn everything from the users, right? So those can come into like, how do you say, work in conjunction rather than like, separately.
Okay, but do you see then this adding of details like a post-processing more than something that can be learned?
I think it has to be sort of post-processing because those require some specific application. It's not just about photorealism now. It's more about presentation of the data, right? Of what you're trying to show.
And one final question regarding the model. Can you tell us a bit of how big is the MLP that is being federated? I guess maybe the global part of the model.
Yeah, so I think I have something on it. So basically, I think they're very small, like MLPs. They're like eight layers or something, with like one like nonlinear layer at the end. So they're very, very small, but they are like, so in this case, they're separated into three parts. One is the global MLP, which has the position part and the view direction part. And then the second is the personal MLP, which has the personal embedding. And then it's basically they are like three of them, but they are like very, very small. But if you increase the number of like, if you increase the size of your thing, you have to include more and more MLPs, right? So people have shown killer nerves or block nerves and even algorithms after that kind of like do at like a large scale. So that then you have to like either increase your MLP size or distribute your MLPs, right?
Yeah.
Also, this is, by the way, this is basically NeRF in the wild, but running for one particular user. So the actual MLPs are from NeRF in the white paper.
Mm-hmm. Okay, cool.
Actually, we're running a little low on time, but I'll just take this one question. And essentially, the user saying, wow, this is very cool. Can I use this now? Is it ready? So I suppose this question is more about, an open sourcing or someone you're showing some interesting rendering here based on some images. So like, I guess it's more of an engineering question. What's left to be built out, or could you speak to some of those issues?
That's a very interesting question. I also want to talk about this because I think my perspective on this particular problem itself is that, yeah, I mean, you can use it and you can improve the NeRF algorithms slightly to get better quality, and then you can sort of implement it out. The interesting issue is data. I don't think if I were to do this today as a startup, it would not work because I would not be able to get data from people that easily. But I think at the same time, like Google Maps, or like Apple Maps, if they want to improve some of the features that they have already access to these data because the photos that you have in your camera is always shared with your Apple Photos or Google Photos map. So they might be able to like sort of come up with like technology on top of their current layers of like UI to sort of like enable like better renderings of their immersive views and stuff.
But I guess, yes, I agree with you. There's kind of a cold start issue, meaning you need enough users to be able to build these images. But from a software point of view, does the code that allows you to build these representations, does it work on a phone? Or I guess these are all server-based
Oh, okay.
things?
Sorry.
Or...
I think that's so basically these don't work on phones right now. So they were implemented using Flower Labs, but they actually run on GPUs right now. So what they have is what Flower Labs, Flower, like the library does is basically separate out my GPU into like multiple clients. And now I simulate sort of these clients as like, they actually exist in the real world, but they're actually all simulated. So I think deploying them, I think this is why I chose, I think our Flower is because it's an open source library and there's like, actual implementations that, we can sort of do in user devices, but I haven't looked into it right now. So maybe something, if somebody wants to take over and like wants to do this, I think that'll be very, very cool.
But the models you've trained, the input to the models are I guess pixels, right? And then they produce there's nothing, there's no kind of missing pieces of the pipeline that's being kind of approximated. Or
no, nothing. It's all done, but it's all simulated though. Like it's not
Sure,
done.
sure,
So
sure.
I all the data is on my server. And this one server has like multiple GPUs, and then we can split the GPUs because flowers, let's allow that.
Sure,
But
sure, I
all of
understand.
data is sort of like, but yeah, no one user can look at other users' data. It's kind of like split in that way.
Yeah, okay, interesting. And did you open source the code, or I guess because just
I think I'm about to in a couple of weeks.
okay, that's cool. Great. I mean, it'd be cool to see what people build on top of this and kind of start to do their own thing. But
Yes,
yeah, great piece of work.
Yeah, thanks a lot.
Awesome.
Yeah.
Great.
Okay, I think I'm done sharing. Thanks a lot for letting me talk. I think it was very interesting to hear everything.
No, totally. No, thank you for contributing. Yeah, thank you so much.